Okay. In the name of God, the compassionate, this is the second part of the second week of our introduction to C++ template metaprogramming. I ended the previous session by telling you that, well, you know what? There is that possibility of doing all the is prime template metaprogramming. Oops, I'm going in the wrong direction. The is prime template metaprogramming, which is based on classes or structs and their specializations. It is possible to do that with ordinary functions. Well, all you need to do is to define the function or label the function constexpr, right? And well, as soon as you do that, provided that the parameter that the argument that you pass for the parameter of that function is a compile time constant, then you will get your response of that function at compile time. And you can even make that replace this constexpr here with a const eval, and then you will get you can only use this function exclusively at compile time. So one thing though, the thing is that these constexpr functions and the const evals and all that, they came to this world because the C++ people noticed that essentially C++ and C++ TMP are two different languages. And one of the most irritating things for them was that learning the two together means learning two different paradigms. And most C++ people find recursion difficult. So even though recursion is completely still possible using constexpr and const eval functions, it's not the mainstream usage of constexpr and const eval functions. Nothing though stops you from implementing your language in a functional manner. Now, so it is very natural to ask, why at all would we want to use the template metaprogramming? Why do we want to obtain those pieces of information at compile time? Well, I told you about some of it. I said that the mindset in C++ community is that means money, because it means speed, because you have pushed as much as you could to the compile time, and therefore you have less runtime, and therefore your code will win against your competitors, and that means you get the money. So now let's see an example of where and when that might actually be a source of money for you. So let's say that you have a function foo, right? That well, inside of it, it wants to do something with an array of size sz of t's. Now, that's this array of size sz of t's. Now, well, first of all, this array guy is not the C array. So like this, we're not speaking about this or this, which is the fixed length array, right? This is what is referred to as stud array that we're dealing with. This is a C++ thing. and it has a number of throws on the C-style array. Now, we're not going to get into the differences. Now, let us suppose that your the way that you handle the logic of foo can be different for, let's say, performance reasons, based on whether or not this SZ thing is a prime. Right? Now, you can get benefit from that by doing this. So you provide, and this is just one way of doing it, and it's a relatively older way to do so. You say that, okay, I want to put the logic in this struct called helper. Now the helper gets a SZ non-type template parameter, which is for the size, and then it checks to see whether that SZ is a prime. If it does, then it has one logic, and if it doesn't, it has another logic. You know, now these two, the one on line 4 and the one on line 6, they are specializations of the main helper struct for the values true and false. Right? Now, you see the logic is awfully scattered around. It's, you know, you don't have a simple if statement which tells you, okay, here is the logic that you have to. Well, first of all, you have to go through this you know, helper function. Sorry, helper struct, not even a function, right? Helper struct, and then you have to have two specializations. Now, this was a repeated scenario, and so the people in C++ before C++ 23, before C++ 17, they had come up with abstractions based on the available support, linguistic support, right? Now, that abstraction is enable if, right, which works on top of something called INF329A, and nowadays you should try to refrain from that because the readability is awful, unless for a specific reason that I will tell you later. Because that the reason why you can now refrain from that is because now C++ has this compile time if that I have already told you about, the if const expr, right? And there is by the way, I also told you about if const eval. Now, what I told you was wrong. I would tell you the correct version. I do apologize for that. So, okay, well, INF329A is an acronym. It stands for substitution failure is not an error, right? And it well, first of all, this is I do apologize for this being a mental torture. You know, it was not designed to be a mental torture. It was the only way that people could get something that they really wanted so hard out of the available linguistic support in C++, right? But given that it's a torture, you know, if you ever going to get used to it, it takes time. The syntactic noise in that is absolutely enormous. And so this is very common, at least for the, you know, pre C++ 14 and C++17. So if you have legacy code, chances are very high that 329A is in there. And like I said, there are occasions where this is still the only solution. Now, given that you are going to scare people with your C++ TMP in your CVs, this is something very scary. So we're getting close to Halloween, right? So you should now have your costumes on. Now, so let's say that we have a function called len, right? That is supposed to work out the length of the array, or sorry, the objects that it is passed to, right? Now, we have three overloads of that here. One of them works with arrays, C-style arrays, right? So that's this one, the first overload, right? It says if I am passed an array of size n of type T by reference, my apologies for the syntax, then I am going to return in, oh, Jan had left. I didn't notice. Okay. Then I simply return the compile time constant n, that is one of the non-type template parameters that is passed to the function. Now, I have to tell you that T and N here are automatically deduced by the compiler. So if I for example have int a5 and I pass len, I pass a to len, the compiler will automatically deduce that T is int and n is 5. Now, you should know that this n here is a compile time constant, and so it is in fact here. And that's that's the only reason why you are, so it is because this is compile time constant that you can pass that array to this overload of the function. Now, it would be a syntax error, if possible at all, if we would have wanted to pass that a thing at the top to the second overload, because then the substitution of the type of array, or the substitution of the little a for this T, would cause syntactic trouble, because a here has no size member function, right? However, you will not get an error message if you perform this call, because substitution failure is not an error, because the overload resolution mechanism of C++ understands that this is a better fit, and it does fit, right? And well, this one doesn't, the second one doesn't, but that's fine. It will not try. Therefore, you will not get an error. Now, people employ this lack of error as the way for them to realize, to kind of inspect at compile time what exact type they are receiving. Right? Now, so in this very case, there is also a fallback function, which is this third overload, right? Which says for everything else, I am going to return 0. Now, this thing is what is called ellipsis of C, or C ellipsis. It comes from the programming language C. It is inherited from C. This will match everything. And by everything, I mean everything, and it's not type safe. This is still a variadic function, but it's not a variadic template function. Now, C does support variadic functions, but because the variadic functions can accept anything, well, any number of anything, and they are not type checked, it's not type safe, right? Now that's why in general you should stay away from it. All right. Now, my apologies. So let's see some examples. If I pass this A up here to A, then I'll get the best match for me would be the C array thing, right? Now, given that this is also an instance of const char star, which can implicitly, in this case, be converted to, sorry, const char 3, right? If I perform the second call, which is on line 3, I will still get the first overload. Now, vector is not a built-in array, a C array, right? But it has that dot size, right? And sorry, one more thing is that it has, so vector of every T has a nested type declaration called size type, right? Whereas that is not available for C arrays, right? Now, if we would have wanted to substitute C arrays for the second overload, then we would have been stopped right at this point where we are dealing with the return type of the function, because there is no nested type definition size type for built-in arrays. My apologies for the wrong direction taken all the time. And so if I have a raw pointer that I send to len, right? Because neither of the two first overloads match, then I get to go to the fallback, and I don't receive any error messages that, wait, I wanted to check the first two overloads and they didn't match, because substitution failure is not an error, right? Now, here is something more interesting. You see, come on. the matter of choice of the overloads here takes place according to a few things, including, or well, maybe I should say it this way, is based on the signature of the function. So we have three signatures here, right, and three bodies, right? Now, C++ decides on the overload of its choice based on the signatures and not based on the bodies, right? So if it is the case that we have a type that does support this nested type name, and the other overloads are not better matches for the reasons that is obvious. So if it has this, then this is the least specific. This is only the fallback. This is the least specific overload. If it does have this, then that's a better choice. That's a better match, right? If there is a type which does support this bit of syntax, but does not support this bit of syntax, then the substitution takes place, but produces an error, because the substitution is based on the signature, not based on the body, right? Now, here's an instance. Come on, again. Right. There is something called allocator. You don't need to know about it at the moment. Well, in fact, I don't think we will ever get into it. But it's essentially the mechanism for the C++ containers to manage their own memory, and the programmer can have a say on that. Now, let's see. Now, this allocator thing does support that colon size type, which means that out of the three overloads that we have provided, the second one is the best choice, and the substitution therefore takes place. But because it doesn't have the size member function, for reasons that if you knew what allocator was, then you could have understood yourself, but doesn't really matter. The body of the function will fail to compile for allocator. Now, we don't want that to happen. Here's one way to do that. This is perhaps quite complicated. I do apologize for that, but it's we'll get there. Before I explain to you everything, recall that there was this keyword that you use as the return type of the functions when you want the compiler to perform the type deduction for you. So you don't want to be very specific about the return type, right? Recall also that there is this right arrow some type that you can put, so that you can help the compiler. You can guide the compiler about the type that you possibly want. Now, there is here from this point on. No. I had already told you about decl type. So, right, where did I do that? Oh, I have it here. Right. Oh, here it is. So the second overload of max makes use of decal type by providing an expression. And why is that useful? Because it's saying that, well, the return type of this max function will be the type should have we wanted to give this a type, the type that we would have declared this expression to be of, take that type, that's the return type that I'm after. And I told you that you can simplify this expression because the value here is not important. It just suffices that you provide a Boolean and you can simplify it, right? The return type will be the same. Daniel is close to giving us a yawn. No? Yes, okay. Now, so that's our flashback for decal type. Now let's get back to where we came from. Now there is something called well, sorry, for sequencing of expressions, you can do something very strange in C and C++, which is using the comma operator. So if I say that, I don't know, int a equals, let's say, 5 plus 5 in b times 2, then, I don't know, 0. What will happen is that a will be 0, but before returning 0 from this expression, before reducing this expression to 0, these other expressions will also be evaluated. And I see some eyebrows raised. That is a very natural reaction, right? Now, my apologies that C and C++ are such strange languages, right? Now there are, I'm not going to get into that, but there are performance reasons, right? Now, so with that in mind, we can decipher what you get here. What this is saying is that, okay, the type that we will be after will be the declaration type of this thing, which, by the way, this is an instance. So you see these extra pair of parentheses at the end. That's instantiation. Right? It's instantiation. Suppose that that's true. So it's saying, give me one instance of this type, and then it's saying, okay, I want the type of that instance, which would essentially be the same as this guy, right? But what it's doing before acquiring that instance is that it's saying, well, this expression, let me change the color. Okay, I'm going to choose red now. This expression should also be valid. Now, well, because it has to reduce, I told you that when you have a sequence of expressions comma separated, all of them will be evaluated until the very last one is returned, and evaluated and then returned. For them to be evaluated, they have to be valid expressions, right? Now, let's delve into this thing. So in order for this to be, valid, this part of it, which is the core of what we want, needs to be valid. But there is also C-style conversion to type void here, because if you don't do that, then this thing might return something of a type T for which the operator comma is overloaded, which means that there is the behavior of this comma will no longer be the behavior that we are betting on. My apologies for all that. I know that this is such a mental, yes, torture.
I miss Idris.
What was it? Sorry,
it makes
you
complete
missed it, yes. I can see why. I can see why.
All very
I mean, it makes complete sense. Don't get me wrong. It's just like it reminds me of this time. Like I had a really bad headache and I slept really badly.
Oh, I'm sorry to hear that.
And I needed to wake up quite quickly for an exam.
Okay.
And I sort of slunk to the fridge with I kept my coffee in the fridge at the time. And I opened the fridge door and got this tin of coffee because I needed to wake up quite quickly. And I, in my tiredness, dropped that coffee and it hit my toe. And that woke me up. and it's this reminds me of that moment where I was kind of like, well, the coffee did wake me up, but it did it in the most unpleasant, like sideways. Like it makes sense, but it's just
yes. And you see now, if you had done that intentionally because you needed to wake up, and that was the only way that with the support that was available at your home was possible, then you would have been doing this template metaprogramming.
I think I would have stayed a C developer.
Well, fair enough.
No,
fair enough. But you
joking.
see, C++ people are so desperately
trying to not be C++ programmers that they've created a new language on top of it.
Well, let me.
This is a cry for help, Hossein.
Yes, that's true. That's true. So C++ people were so desperately after after leeching this amount of runtime out and putting it into the compile time that they did all these crazy things, and that brought it to the attention of the committee, and that gained weight so that nowadays there is better support for this thing in C++ 23. But it had to be that the community had to have enough usages that they were desperately working for so that they could finally get good linguistic support. So the evidence had to be there, and this is such an evidence.
My question is though, just it's more a question of humanities, if you like. It's a slightly sidestepping question, but it's is this a response to the complexity added by objects? Because we have so much usage of C, and there's been no drive to change it radically.
Rewrite it in Rust.
So are you speaking about backwards compatibility?
No, I'm saying like C people don't seem to. I mean, I'd love generics in C, but in all of the C work I've done, and I've done a lot of kernel work, there I accept that there's been absolutely no use for it at that level, and the kinds of performance we're hitting is fine. It's these are very optimized programs, but my question is, like, you have this when you add classes, you have these layers of abstraction, which definitely confuse performance. Because like when I'm stepping through C code, my call stack is never more than like 3. And when I'm stepping through C++ code, my call stack is never more than 50 or never less than 50, because there's so many standard library calls and issuing. And so I wonder if this is a response to the complexity of reasoning about things. You need stronger tools to reason about object-oriented code than you do would normally.
No, because it's you will not be able to get this kind of compile time control in C at all. You essentially don't get anywhere close to it. There are no templates. So there are no you mentioned generics. You mentioned generics. I don't think that is a very precise use of terminology.
No, it's not.
There is no type level programming. There is no
I know. I get it.
Avoid,
C is no. That's not my point. My point is the motivations behind this development. That's my question.
Yeah, the motivation is to stay type safe and efficient at the same time. And so there are loads of things that C++ can do, which C cannot.
Yeah. Without a doubt, that's not my question.
Yeah, and let me finish. And by doing which, the C++ code becomes even faster because it gives the compiler more information for optimization. It's not that the compiler will, well, because C, converts everything to void pointers and all that, and doesn't perform any checks, therefore it's faster. It's that the C++ knows the types that it's dealing with, and therefore, can perform optimizations at compile time, and therefore it's safe not to, do type checks at runtime, but it has at compile time also done more specific jobs so that it's faster. So they want to be efficient and performant at the same time that they are type safe. That's
sure, but why haven't C had the same push? That's more close to my question.
Right, because it doesn't appeal to them to be type safe and all that.
But the performance does.
Well, the performance does, but they are convinced that that the complexity is not worth it.
I wonder why.
Yeah. Well, it's a matter of choice, it's a matter of taste. Sorry, it's a matter of taste. Thank you for the question. Now I think this was right. So I did promise to you to show the if const expr, right? Now, in fact, I had in the past also shown that to you. So here is an instance of that. This is what in C++ 17 used to be called compile time if, right? Nowadays there's also if const eval, which is slightly more compile time than if const expr, but let me just escape that for a moment. Now, here are a few questions. I'm going to go through you one by one. Jan has been, I think, the most quiet.
Mm-hmm.
Now, Jan, you know that when we put this const expr here, that means that this expression needs to be evaluated at compile time, and therefore if the compiler fails to perform that evaluation, the compilation will fail.
Yes.
And you know that if this expression, the result of this expression means that the compiler knows at compile time which branch it will take, and the other branch will be eliminated by the dead branch elimination optimization phase of the compiler. Now, with that in mind, tell me which phase would, let me maybe use another notation and change the color just for which phase would this line fail in, if at all?
Not in compile time, since well, I don't know what undeclared, or if not declared, no.
Let's say that that's an undeclared function, right?
Right. So if that one would fail probably after compile time, since though it might be a counterintuitive question you're asking here, because constexts will only fail. Oh no, constexts will fail at compile time.
Well, let's say that did fail, right? Which means that this branch is
eliminated, so it goes to the next branch.
Eliminated, yes, that's right. So let's say that the flow of compilation made it to the second branch. And reminder, C++ templates enjoy what is called the two-phase translation. Right? Now, the first phase is when things that do not depend on the template parameters will be checked, and the second phase is the one in which the things that relate to the template parameters will be checked. Now, all of that is in compile time.
So that's second phase, since the T is related to the type parameter.
Very good. And all of that, both of those phases are at compile time.
Yeah, so it's all in compile time.
Okay. So yes, that is true. This is the second phase. Now, Mikhail, which phase will this one fail if the compiler cannot find this function that we are making call to on line 12?
If the compiler can find it.
If the compiler cannot find this function, let's say we call this f, right?
Yeah. Won't it fail on compile time then?
That is true. Which phase of the translation of the two phase?
Oh, I don't remember the phases exactly.
Phase one is the phase in which the things which do not relate to the template argument, to the template parameters, will be checked. Phase two is the one that the things which do depend on the template parameter will be checked.
Phase one?
That's true. This one, it's phase one.
Ooh.
Yeah. Thank you. Now, Niels, which phase will the static assertion of line 13 fail in?
Phase one?
That's true. That's true. So this is because false is a compile time constant that does not depend on the template parameters. Okay, it's true. Okay, Daniel, which phase does sorry, the static assert on line 14 fail in?
I'm going to go for the second phase, as it's dependent on T.
That's true. Exactly. So because of this T here, the failure of this static assert will be on the second phase. Now, how do we know that? Because we're in this else branch, not in the then branch. So we know that this is well, my this static assert will not fail because we're in the else branch, which means that this condition was wrong. There was false.
There's a negate.
Yes, that's
Yeah.
right. And there's a negation here.
Oh, right. Yeah. That was a small little negation.
I was caught by my own question. Right.
Sorry, I have to grab my charger real quick. I'll be back in 10 seconds.
That's fine. That's fine. Now, so I told you about the linguistic support now being much better, so that you no longer need to do the well, let me go to the slide. Right, here it is. So I told you that nowadays there is better linguistic support so that you don't need to scatter your logic like this as you're doing here. Now, that better linguistic support is if const expert. So now, instead of having to put the two well, first of all, a helper struct, and then two specializations of that at two different places for false and true, I can simply say if const expert is not primed or is primed, or things of that. Now, here is a relatively less obvious question, and I'm going to ask this from James. So even though we are now using linguistic support, which means that the logic of ours will be more clear in this implementation of the function foo, right? There is one level of flexibility that is not present in this implementation and was present in my apologies, the links don't work in Remarkable, so I have to do it manually. But the PDFs that you received, they have links, so you can just go back and forth between two. There is one flexibility that is available here that is not available in the if const expert. Can you spot that? It's absolutely fine if you don't, because this takes some time to sink in, you know.
I mean, I can think of an immediate one that doesn't actually apply in this case. Which would be that, say you are templating for a class. So say you're making some type where there is an optimization if you're modding by a prime. Then you can at least completely redefine that class. Different internal variables, different methods, etc. Like the structure would be the same. It's not just a part of a function that's different. In which case you couldn't just stick the whole thing in a if const expression and have one class declaration and then another one somewhere else. But
well, that's a special case. That's a special case of the response that I would have given to this question.
Okay, if that's a special case,
yes, but that's along the, you know, you're on the right track, right? But there is more to what you just said. Now, imagine that this, instead of being a bool, was, let's say, an on-site int. right? Now, I could have had more than just 2 specializations then, right? And the thing is that this way, the specializations were open-ended, which means that the next programmer could have added their own specialization, and their specialization would have participated in their part of the world in the overload in the specialization resolution. Jan, was that you yawning? Okay. Right. So, okay. Whereas in come on. In this implementation of foo, the if statement is inside here, and the user of foo cannot manipulate the behavior of foo by providing new specialization. It's a close-ended implementation. Whereas that implementation, the previous implementation, is an open-ended implementation. Now, what the lesson to take is that still, even though this is a much more clear implementation of your logic, if you want to give your user the possibility of manipulating the logic, you want your implementation to be open-ended, that implementation still, unfortunately, is your method of choice. Now, who's following? Who's not lost? Okay. Okay. Sort of. Okay. Well, Niels, before you tell us where you're lost, give us the joke that you owed us.
Okay. I used to really hate facial hair, but then it grew on me.
Okay, well, I can see that. Yeah, good. I mean, this is does the translation of that in Norwegian work?
No.
No.
You
Okay.
could probably phrase it a way that it worked, but I don't know Norwegian enough.
Ah, okay. You have an accent, you said the other day.
Yeah.
Okay. Right. Fine. Now, Mikhail, give us your joke, please.
Oh, why did the programmer quit his job?
Oh, again.
I know this one.
Oh,
What was it? Sorry.
why did the programmer quit his job?
No. What was the response?
Because he didn't get a raise.
He didn't what? Sorry.
He didn't get a raise.
A raise.
A raise.
Ah,
Yeah.
okay.
All right, yeah.
Okay, I see. Okay, so the previous time the programmer had gone bankrupt
Yeah.
because they have lost their cash, and now they quit their job because they didn't get a raise. Okay, well,
It's the
looks
same
like the programmer is having a tough life.
Yeah.
Okay.
It's because of Chat GPT.
Yeah, God forget. Yeah. Okay. Let's no, it's sorry, wrong expression. God forbid. Now, where in what I just explained, are you lost, Mikhail?
Just I think it's the syntax of C++ in general, so it takes a little time for me to comprehend.
Poor you. Okay. Oh,
But
I'm
I
really
understand the
sorry.
concept, but yeah,
Okay.
it's
Okay.
He needs some
I
time to
should,
parse.
yeah.
Oh, I see. Okay. Well, then my padding and your back. It's
Thank you.
I'm really sorry to give you this difficulty. But remember, you're gonna scare people with this.
That's the only
Okay.
reason you get new C++ developers, because then they can create the code that other people are scared of.
No, because they can do things which the other people cannot do, and
It's called
and
job
they
security.
Yeah, I mean the loads of reasons. Now, we are done with this much. So we're done with the oh no, I don't want to. Oops. With the slides. Now we can finally go get some real C++. Not the ones
write some
that
text in
we
the
have
computer.
been seeing on the slides, the ones that you will get your hands dirty with. Right. And I think I can stop the recording.